Welcome to the fourth video on first order step responses. This particular video is going to focus on sketching, but first let's revisit some of the results from the earlier videos. So we're going to consider a system which can be modelled by a first order differential equation with constant coefficients. And so without loss of generality, we can write this in a standard time constant form, as you can see here. So we've got t, capital T, dx dt, plus x of t equals capital K u of t. And the key coefficients are the capital T, the time constant, and the capital K, the system gain. Now what we've shown in earlier videos is there's an analytical solution to this, where u of t is a step. So if I assume that u of t is a step of magnitude capital A, then the analytic solution is given by x of t equals x of 0 minus ka, all times e to the minus t over capital T, plus ka. So what do we want to look at? We want to look at the behaviour of x of t for t positive when u of t is a step of magnitude A and for non-zero initial conditions. The key thing is we're going to look at the sketching and see how these sketches change as I change capital T, change capital T, K, and of course change the initial condition. So here we go. Before we start, we want to extract some key observations about the system behaviour. So you'll notice I've put in the top right hand corner of this screen, right up here, so we don't lose it, what is the solution we're looking at? X of t equals x of 0 minus ka e to the minus t over t plus ka. What we're going to do is look at this solution at specific times. So the times are going to be t equals 0, capital T, 2 capital T, 3 capital T, and so on, because that is those are the key points that we might want to use in order to get our sketch. So first, let's have a look at t equals 0. Now, what I've done first is extracted the exponential term. So if you look here, under here, you'll see I've extracted the exponential term x of 0 minus ka e to the minus time over capital T. And because time is 0, that becomes x of 0 minus ka, and I'm going to give that a value d. Now you'll notice that d is quite significant, because when I go over here and have a look at what I've got for x, you'll see x equals ka plus d, and that, because time is 0, equals the initial condition x of 0. Now what's interesting is that comprises two terms, ka and d. And ka, we'll know from the earlier videos, is the steady state. And so therefore, this x has been written as the steady state plus a distance from the steady state. So we know how far the initial condition is from the steady state is given by this term d. Now let's see how this expands when we go to the next time instant, which is capital T. So here we go. At capital T, we can now do some analysis, which you'll see is given there, that x of 0 minus ka e to the minus t over capital T becomes 0.37 times x of 0 minus ka, or, if I put it here, the value of x at time capital T is ka plus 0.37d. So again, I can write the x as the steady state plus a deviation from the steady state, and that deviation is 37% of d, i.e. 37% of how far it was at the initial condition. So that's really valuable, because I can picture it in my head. If it started so far away, after capital T seconds, is now 37% of that distance. Now I can follow the same logic if I go to time equals 2t, and you'll see the expressions derived here, and what you get down here on the right, you find that after 2t seconds I'm now 14% away from the steady state. So x of 2t is ka plus 0.14d. And finally, I can look at 3t, and here you'll see I'm down to x equals ka plus 0.05d. So hopefully you'll see there's a very neat pattern here for how x changes with time. The steady state appears in all these solutions, x of 0, x of t, x of 2t, x of 3t, and the actual values are written as the steady state plus some distance from the steady state, and that distance starts at d and then goes 37% of d, 14% of d, 5% of d. And this will make it very easy for us to do a sketch. So here we go. We're going to do the sketch, and we note, as we did in the previous videos, that the response is invariant if you mark the horizontal axis in terms of capital T, so as 0, capital T, 2t, 3t, 4t, and then all the derivations we've done follow. So we use the coordinate pairs that we've just derived. The initial condition is the initial condition, fine, but then we calculate this value d, which is the distance between the initial condition and the steady state. So d equals x of 0 minus ka. And then what we can do is we can calculate x of t as ka plus 0.37d, x of 2t as ka plus 0.14d, x of 3t equals ka plus 0.05d, and x of 4t equals ka plus 0.02d. Having done our sketch using capital T as the horizontal axis, we can always then scrub out the capital T and put in the actual values of time. Okay, so the next slide will illustrate this process using a very simple example. So here we go. We've got an example, 2 dx dt plus 6x equals 4u, and the initial condition x of 0 equals minus 1. So first we need to note the time constant. Now, if you're wondering where that time constant's come from, what I'm going to do is divide the whole equation through by 6, and so what I'm going to get is 2 over 6 x dot plus x equals 4 over 6u. So what you can see is the time constant is 2 over 6, or a third, and also the system gain k is 4 over 6, or 2/3. Now because I've assumed we've got a unit step, then I'm assuming that capital A equals 1. So therefore I've got ka equals 2/3. Right, observations. We can see that the curve begins at minus 1. That's given there. And the other thing we've been given is the curve finishes at 2/3. That's that observation there. And therefore we can work out this distance d, i.e. the distance between the steady state and the initial condition, and this is the calculation given here. X of 0 minus ka is minus 5/3. Having done that, I can now say, okay, where will it be after capital T seconds? Now we noticed that it was 37% of the distance it was at time t equals 0, so I need to calculate 37% of minus 5 over 3 and add that to the steady state. So if you look at this calculation here, okay, you'll see what we've done is you've said x at capital T, which is x at a third, equals 2/3, so that's ka, plus 0.37 times minus 5 over 3, and that gives you this answer here, 0.05. The next line 4 is I've done t equals 3t. Okay, so you'll see I've got x of 1 down here equals 2/3, again that's ka, but I've done 0.05 times d. So it's 0.05 times minus 5 over 3, and I get 0.58. So you'll notice I've simply carried out the computations as indicated on the previous slide. And now all I need to do is put them on a sketch. So if you look over here, you'll see I've got x of 0 equals minus 1, the initial condition, x of capital T is 0.05, x of 1 is 0.58. So if I show you where I've marked these, there's x of 0, there's x of capital T, there's x of 3t. And down here, if it wasn't clear, I've got t, 2t, 3t, and so on. And the steady state is clearly marked over here as 2/3, or 0.67. So all I'm going to do, once I've got those points, is draw a smooth curve which goes through those crosses and finishes at the steady state. So here's another example for us to try. So we'll do the steps again in a systematic way so that you get the idea. So first of all, put the system into time constant form. So what am I going to get? I'm going to get 6 over 4 times x dot plus x equals 3 over 4. So I've got t equals 1.5 and ka in this case is 0.75, 3/4. The initial condition is given above, it's at 2. Next, compute the steady state and the initial distance d to the steady state. So I've already got the steady state, but now I can do x of 0 minus ka equals d equals 2 minus 0.75, which equals 1.25. So there we've got d. Next, it says compute the values of x of t and x of 2t. Okay, so what we're going to get, make sure we've got space here, is x of t is going to be, now we need the steady state, which is 0.75, and then we're going to get plus 0.37 times 1.25. Now, I'm going to need my calculator to do this, so we've got 0.7, what have we got? We've got 0.37 times 1.25 equals 0.46 plus 0.75, so we get 1.21. Okay? And then if I do x of 3t, by all means do x of 2t as well if you want, but you may find that that's often not strictly necessary. So x of 3t, you get 0.05 times 1.25. And you can probably just about work that one out. It's going to be about 0.06. So I'm just going to do this in my head and say you've got roughly 0.81. But you can check that yourself if you're not convinced. Okay, so now I've got the key values that I need. So if I mark these in red, just so that we notice what they are, we've got the steady state, there it is. We've got the time constant for marking the horizontal axis, we've got x of t, and we've got x of 3t. So now we move to the sketch. So here we go, a nice blank slide so we can do a sketch. So I draw my axes so I can see what's going on. And I put on here t, 2t, 3t, 4t. Now I'm going to need to mark the initial condition, which was 2. Let's put some scales on if that was 1. And then the steady state was 0.75. So let's put that across. So we know where we're settling and we know where we're starting. So I'll now use red to mark the individual values that we got. So we started there. Now where were we after t seconds? We had 1.21, so that's going to be approximately here. Where were we after 3t seconds? We had approximately about 0.8, so that's going to be about there. And so now we've got our curves, our points, we've got our steady state, so we get a nice smooth curve, and there you go. There's our sketch. Now finally, you might want to put in what exactly was the time constant, and remember the time constant t was 1.5, so I can put under here 1.5, 3, 4.5, 6, and so on. Okay, that sketch isn't too bad, but if I wanted to be pedantic, I could say, well, a mistake that students often get wrong is the initial gradient. And it's actually very easy to get the gradient a bit more accurate and therefore make your sketch slightly better. So here's the analysis you need. What I'm going to do is take the original analytic solution here on the left, x equals x of 0 minus ka e to the minus t over capital T plus ka. I'm going to differentiate it because that will tell me the gradient. So dx dt equals x of 0 minus ka over minus t e to the minus t over t. And finally, I'm going to evaluate this at time t equals 0. And what do you notice? It's minus d over t. And this is interesting because d, of course, was the distance from the initial condition to the steady state. And you also notice in the denominator we've got this capital T. So you end up with a very interesting observation, which is if you draw a straight line through the initial condition x of 0 and x of 0, then what you find is if you follow the gradient from that point, then after capital T seconds you get to the steady state. Okay, so you follow the gradient from the initial condition for one time constant and you get to the steady state. And so that's a very, very easy line to add to the plot. It'll be more obvious when we do some examples, but you can follow that analysis more slowly if you really want to prove it to yourself. Okay, and what we're suggesting is you add this line to the plot before you do the sketch, because it makes sure you get the initial gradient correct. So here's an example. What you can see is that we've got a time constant. Let's put it down here. Here. So the first time constant is this line here. The steady state is this line here. So if I put that point, hopefully you can see what I've done, then all we've done is we've drawn a line from the initial condition to that point. So basically we get to the steady state in one sample instant, we draw a straight line between those 2 points, and that gives me the gradient at x of 0. And hopefully you can see that this blue curve does indeed follow that gradient. So what we're suggesting in general is, after you've put on your red points, which we did earlier when we did the sketch, we just did those red crosses, we're saying first add this straight line to make sure that your initial gradient is correct, and then your curve will be just that little bit better. Okay, so summary of some of the observations. We've said if you have a standard first order model, t dx dt plus x equals ku, and you assume that u is a step of magnitude a, then the solution is known. It's ka plus x of 0 minus ka e to the minus t over t. Okay? The response follows an exponential decay from the initial value to the final value. The time scale is determined by capital T, which you'll notice is one of the parameters of the differential equation, and the points for the solution at time constant t equals t, or t equals 2t, or t equals 3t can be determined and are fixed as long as you do them in terms of this time constant. So you have, as you can see here, 0 x of 0, or t ka plus 0.37 times x of 0 minus ka, or 2t ka plus 0.14 times x of 0 minus ka, and so on. So if you recognize that this is invariant, these observations apply to all first order differential equations of this type, then you can draw an invariant curve and then just put your fine details on, like defining exactly the capital T and so on later. The other observation, just to tune things up a bit, is the initial gradient reaches steady state in capital T seconds. Alright, a few simple slides to finish off. What we've done is we've gone from the differential equation to a sketch, but actually, as was pointed out in the previous video, you can go the other way around. If you've got the response curve, then you can very quickly estimate the parameters of the underlying model, that is the time constant and the gain. Okay, so what sort of observations do we know? Well, we know the step response moves 63% of the way from the initial condition to the steady state in capital T seconds, and also 95% in 3t seconds. So we can use that observation to estimate capital T. The gain is the ratio of the steady state output to the size of the steady state input, or the step input. So it's relatively easy also to estimate the gain. Now, these calculations rely on the assumption that the curve comes from a first order model. So before you use these observations, you need to have enough engineering insight or knowledge about the process to say that you're confident that the underlying dynamics and behaviour is governed by a first order model. If that's not true, then using these observations will not really help. So an example. I've got a curve here, and what I'm saying is, okay, given that curve is a step response curve from a non-zero initial condition, what do you think, okay, the parameters of the underlying model are? What's the time constant and what's the gain? Now, we'll assume that this had a unit step input because it doesn't say otherwise, and I think that's a fair assumption in any exam. If they just say a step input and they don't specify the magnitude, you might just want to say, I'm going to assume the magnitude's 1 because you haven't told me. Now, if you look here, you'll see we've got a steady state, or let's rewrite it as Ka equals 0.8. If we assume that A equals 1, that gives me K equals 0.8. And you'll notice from the proposed solutions above, that means it can't be this one. Okay? Right, next we want to get the time constant. To get the time constant, we're looking at a 63% movement. So let's work out what this distance is. So I've got a distance here. It finishes at 0.8 and starts at minus 1.5. So the total distance is 2.3. Okay? So if I do 0.63 times 2.3, and again what I'll do is I'll get my calculator just to make sure that I don't do this in a stupid way. Then I get 1.45. Okay, so after t seconds it's moved 1.45. Now it's starting from minus 1.5, so if I do minus 1.5 plus 1.45, I get 0.05, so with a minus. So that tells me that after t seconds I've got to minus 0.05, which is going to be this line here. So that's minus 0.05, and so what that tells me is this down here is capital T. Now I can't be overly precise, but it's of the order of 0.7. I'll let you argue about whether it's 0.7 or 0.65 or something similar. Remember, we're only doing estimates, so don't try and do it to lots of decimal places because it's a bit pointless. So there we are, we've got 0.7 and 0.8 are our estimates. We now look at the proposed solutions that we've been given up here, and you notice that one of those proposed solutions is very close, so that must be the correct one. T equals 0.67, K equals 0.8. Alright, here's another example to try, and I'm going to do this one a bit more quickly, because hopefully now you've got the idea. First I look at the steady state. So Ka equals 5. Again, I've not been told that the magnitude of the step, so I'll just assume that A equals 1, and therefore I get K equals 5. So the first bit, very, very easy. Just look at the steady state. Now, next I look at the total movement. So the total movement here is 20. So after t seconds, I will have moved 0.63 times 20, and you could probably just about do that one in your head. That's 12.6. Now, where does 12.6 take us? So if I now do 25 minus 12.6, that gives me 12.4. So I've now got to find the value 12.4, so I'm going to do that across here. So there's the value 12.4, and you can see it intercepts here, and what we're saying is at this distance the movement, which is 63% of the movement, is 12.6. So I've moved 12.6 from the initial condition, and that's 63% of the way to the final condition, which is 5. And hopefully it's clear that in this particular case t equals 50.